Okay, definitely.
Okay, good. So let me begin by thanking the organizers for the very nice workshop and for the opportunity to speak here. Today I'll be talking, I'll give a brief introduction to D-instantons. It'll be mostly based on these two papers in the context of C=1 strings with Bruno Balthasar and Shi Yin, and also some work in progress in type 0b string theory, also in 2 dimensions. And then in 10 dimensions, in the type 2b, with some reinforcements with Nathan Agmon and Minjae Cho, who will be speaking right after me. Okay, so let's get started. We want to see how to compute non-perturbative corrections on top of the usual perturbation theory that we learn in textbooks, depicted here, and the loop expansion of the closed strings. So we have the closed string coming in, say coming out. And we would like to see how to obtain non-perturbative corrections in GS on top of these loop expansion. And the way to do this is a bit similar to D-branch scattering. So we have to consider Wolsche diagrams with a boundary, like in here, where the boundary is the so-called D-instanton. And these are generally boundary conditions that is of Dirichlet type for all space-time coordinates. So all non-compact directions will have a Dirichlet boundary condition, including time, which is the important one. Okay, so the first important aspect of this is that we should consider disconnected diagrams. So in fact, the leading order contribution is not the one I drew above, but rather these disk 1-point functions, because there's one factor of G string from the vertex operator, as the usual convention. And the disk topology has a normalization factor that goes as 1/G string here. So the whole thing goes as order 1. So this is the leading contribution. And it's disconnected, but the two boundaries here and the two different disk 1-point functions is the same D-instanton. So a nice picture to have in mind is right here on the right, that the D-instanton occurs at one specific point in space-time. Let's say it's x1 vector. And then the closed string comes in and it goes out in space-time. So this is the picture I like to keep in mind. So the time, the space-time point at which the instanton occurs is called a collected coordinate. So as we see, the instanton itself breaks Lorentz invariance. So importantly, we don't expect an individual diagram to conserve energy momentum, but rather it's only after we integrate over this collected coordinate that we recover energy conservation. So after we compute all this 1-point diagrams, we must integrate over the collected coordinate of the D-instanton, and then we restore energy conservation, as we'll see explicitly later on. But this is the basic picture. Okay, a second aspect that is important is once we know that we're supposed to include these empty diagrams, sorry, these disconnected diagrams, well, an obvious class would be empty diagrams. For example, we have an empty disk here, or 2 empty disks, or 3 with appropriate symmetry factor, or cylinder diagrams. And in these pictures, all the boundaries here lie on the same D-instanton. So as we can see, these these exponentiate nicely for every Euler number into this expression right here. The empty disk, the empty cylinder, the 2-hole disk, and so on. And they factor out of the Wolsche diagrams were with punctures, where the closed strings come in, the closed strings come out. Okay, and this is a nice interpretation. So as we said before, this topology comes with a normalization factor that goes as 1 over GS. And so this is the one that we interpret as the instanton action. The annulus comes with its normalization factor goes as GS to the 0. So it's just a constant, which we won't be able to compute explicitly. We'll have to fix it through some other means, but it's just a constant that you will fix once and for all, and you can use the same constant for all instanton amplitudes. And then there's corrections. With higher Euler number, for instance, these two go as GS to the 1, and so on. More corrections. And these we interpret as just corrections to the instanton action. Okay, so this is this class of empty diagrams. So now we're ready to draw the leading contribution to the 1 to n closed string scattering amplitude due to a single instanton. Okay, so as we say, that this exponentiated empty diagrams give you the instanton action and the normalization factor. Now the leading order contribution, as we said before, of order 1 is just a product of a bunch of this 1-point functions. And importantly, in the end, we have to integrate the collective coordinates. Oh, the position in space-time in which the instanton happens, and we recover energy momentum conservation delta function. Okay, so it looks pretty simple. As we see, the only ingredient that we need, at least to this order, is just that this 1-point functions of the closed strings in the presence of the D-instanton boundary condition on the boundary. Okay, we're also ready to draw the subleading. Subleading, I mean, due to a single instanton, I mean of order G to the S, 1 over G to the S, times GS. So subleading in this sense. Okay, the worldsheet diagrams are a bit more interesting. So we have the usual exponential diagrams, instanton action times the normalization factor. The worldsheet diagrams look a bit more interesting. So for instance, next order, we have this 2-point function because we have 2 factors from the Vertex operators. And again, this topology, 1 of GS. So this whole thing is of order GS. And interestingly, we have a disconnected diagram for a 1-point function times an annulus 1-point function, which again, this we already saw this is order 1, and this is 1 GS from the Vertex operator, and the normalization factor of the cylinder is the GS to the 0, so it's also order GS. And finally, this 1-point function is of order 1, and we have to bring down some of the corrections to the instanton action, like this, schematically. Okay, so let me here mention something kind of interesting already. So these are not as simple to compute, not just 1-point functions, but one important aspect is that there's a region moduli space where the open string degenerates, as in this picture, for this 2-point function. Similarly for these guys, in this case, it looks like this. So, and similarly for this one. So here, importantly, we will have a divergence due to the collective coordinate propagating here. Roughly, if you want to think of free fields as partial x. And it leads to a logarithmic divergence. Okay. Luckily though, this logarithmic divergence cancels once we add up all the contributions. So the divergence here cancels with the divergence here, and similarly here. Okay, so this is the so-called Fischler-Susskind-Polchinski mechanism, which is the first instance that we see that string theory is smart. So it exactly knows when to save you by including these disconnected diagrams. So this is perhaps a more detailed reason why we actually need to consider disconnected diagrams, because Otherwise, we will have uncanceled IR divergences that will render our theory inconsistent. Okay, but we won't compute this in this talk because it's kind of intense. But let me just mention that since it's a logarithmic divergence, there's a finite ambiguity, and how we regularize in practice. For instance, we put a cutoff. If I use my regularization and you use yours, will differ by a constant additive contribution. But so here it's actually more properly dealt with string field theory, and perhaps Minjae will have more to say in his half hour. So here's a nice invitation for string field theory.
Can I ask a quick question?
Yeah, go ahead.
Yeah. So in Fissler-Susskind, the cancellation happens because the target space background gets modified. I mean, it's like a loop correction. So are you talking about that kind of thing, or is it in?
No. Yeah. So original Fissler-Susskind is what you just mentioned. Really, this cancellation of the logarithmic divergence is due to canceling between diagrams of different topology was explained by Polchinski in his paper. And he called it the Fissler-Susskind mechanism. So that's why we are also calling it.
Oh, I see. So it doesn't mean that you're going away from the standard.
No, we're still in the same vacuum. It's just that there's a cancellation.
Yeah, I think it's just in a broad sense of cancellation divergence between diagrams of different topologies. That's all.
I see. Okay.
Yeah. So more generally, the Fissler-Susskind principle is just that if you find something wrong in string theory, you're the one who's making the mistake, not string theory. So that's it. But Polchinski definitely explained this in the concepts of critical 26-dimensional bosonic strings.
Right.
Okay, that's all we meant. Okay, so let us move past this one.
It is true that the D-instanton is sourcing the dilaton, right? Or is that not true?
Well, in type 2b it does. Here, I don't think so. Here is just a non-perturbated correction to closed string scattering amplitudes. And
yeah, there's no propagating dilaton in single-strand string theory anyway.
Not a propagating dilaton, but okay, but regardless, the source is the tachyon. So I'm just trying to dig into Sumit's question.
Yeah, but the issue here, the divergence is not due to a closed string propagating; it's due to an open string. That's quite different from the Fissler-Susskind original idea.
Right.
Okay.
Yeah, so different. So the FS mechanism is for a closed string divergence, and that's why you have to shift your vacuum. In that case, here there's nothing like that. This is an open string divergence, and as we see, it cancels. So there's nothing going on here.
Sort of similar to cancellation of IR divergences, like in QED, where if you sum, like in a soft photon emission with the loop diagrams, they all cancel.
Well, it is an IR divergence in the same sense, which the open string is degenerating, but there's no, here it just cancels exactly.
I see. Okay.
I think there's no physical propagating open string degree of freedom. These things live on the instanton. So
I think I will be talking about this in the later half of the Basically, it's just that these open string modes are nothing but the instanton moduli modes. So they are not the degree of freedom which is propagating. They are rather the background fields you have to integrate over.
Mm-hmm.
Okay.
Okay, so with this invitation, let's move on to another contribution we can already write down, which is multi-instantons.
Yeah, so it's part of the.
Oh, okay. Multi-instantons. So the picture I like to have in mind is that we have one instanton here, position x1, and the other one here, position x2. Closed string comes in and clustering comes out of the second one, for example. Okay, and the diagrams that we need to compute are the following. Okay, we have the usual factors here. This one, of course, the interpretation that comes from the exponentiated empty diagram on the first instanton plus the one in the second instanton. So we get a factor of 2. In this case, we get the square of it as the exponentiation of the cylinder diagram for both ends and on the same instanton. And then a bunch of, to leading order, just a bunch of disk 1-point functions. And then importantly though, this exponentiated cylinder diagram in which one boundary ends on the first instanton and the second one on the second instanton. Now this one actually depends on the distance between the instantons. So it's a non-trivial function. And this would be, we'll interpret it as the measure in instanton moduli space. So I like to think of this as the two instantons being connected by this cylinder diagram. And yes, so as we see, we have to integrate over the collected coordinates in the end. Okay, one of them, as we saw, the sum of them gives you the delta function conserving energy and momentum. And the second one is just a non-trivial integral that you have to perform. And as we say, this is the correct measure that one has to do. And this can be computed exactly, as we'll do in a second. But this is, let me emphasize here, this is the second instance in which string theory is smart. It tells you directly what the measure is in instanton moduli space, which is this diagram. Okay. So let me just summarize sort of the basic pictures that we've drawn in this. Yes.
But what is fixing that measure? So I didn't get it.
Oh yes, no, you compute it. So you have to compute it. We'll do it in a second, but it's something very explicit.
But just to know, you propose that it has to be the exponential of the annulus, or does the fact that it's the exponential of the annulus comes from some other principle?
Well, no. So this is just a diagram that we have to include in the D-instanton calculus, and well, you can calculate it, and it just gives you the correct measure. This is nothing extra. It's just string theory already tells you that this is it. That this, by the rules that we've explained above, is you have to include it.
Okay.
Okay. So let me summarize here. This is kind of a schematic picture of the structure. Here I really have in mind C = 1 because the one-to-one amplitude literally takes this form and it's non-ambiguous. But let me still say it just so that we put the pictures into our heads. So the first line here is the usual perturbative piece. So the sphere 2-point, and here's the torus 2-point, and here's the genus 2, and dot, dot, dot. The second line is the single instanton contribution. And the first one, for example, is the one that we talked about, just a product of these 2-point functions. The second one is the more interesting one with the FSB mechanism. Also only one instanton, the one that had this higher order, 4-GS here. And then going down the list, we have multi-instantons. For instance, we described this one just in the previous slide, where we have to integrate with 2 instantons. Then also a product of 2-point this 1-point functions, and the interesting measure here. Okay, and of course you can keep going. Okay, so having this picture in mind, at least hopefully the structure is clear now from this picture. Now we can roll up our sleeves and actually try to test this diagrammatic expansion. And our favorite testing ground is C = 1 string theory, which has been introduced already, but let me summarize it here again. So C = 1 strings, the worldsheet ingredients are the following. We have a time-like free boson, which would be time. We have Liouville CFT at central charge equals 25, which is our space, and the usual BC ghosts. So the Liouville CFT is perhaps a thing that's a bit more non-trivial. So it only has scalars over primaries, which I represent as VP, with a so-called Liouville momentum P. And as we know, the OCC bootstrapped all these 3-point functions. So it's very explicit, very computable. And the physical states, the closed strings, are these so-called tachyons, which come with a conventional factor of G string, and then the exponential and the free boson, and then a Liouville Vertex operator with momentum omega over 2 in my conventions. And that's it. Of course, the space-time picture is that we have space here, and these tachyons are just asymptotic states that come in, reflect off the Liouville wall, and come back to the asymptotic region with weak string coupling. Okay, so let me go on to D-branes here. So for completeness, I listed a few of them here. So, so we have the FCCT brane, which is like a D1 brane, which is of Neumann type on the free boson, and of FCCT type, or Neumann as well, in the Liouville side. And it's extended like this.
Excuse me?
Yes?
Can I ask you about your previous slide?
Yes.
As far as I remember, structure constants are not well defined for B = 1. Isn't it?
No, these are
Yes.
very explicit. They're I can write the formula down, but it won't be too illuminating. But no, these are well known.
So analogy with the B goes to 1 limit is that in some sense the Lagrangian description breaks down. So if you want to express quantities in terms of the Liouville cosmological constant, depending on the scheme, it might become singular. But if you express them in terms of the conformal data, they are completely regular and well-defined. And these sort of constants are explicitly real.
Okay.
Yeah, so maybe you were thinking that in this sense, as you say, this is a equals 1 limit of the usual formulas. And so this is sort of, if you want, the strongly coupled region here of the Liouville, so away from the semi-classics. So this way is better to use the bootstrap approach, and these are very explicit functions. Okay, so then now, yes, back to the D-branes. So the FCCT brane is extended, as we will hear more about tomorrow. And then the CC brane, which is of Neumann type in the free boson, and CC type in the Liouville direction, which is Dirichlet type. These reside in the, these are fixed in space. You can think about it maybe in the strong coupling region. And finally, we come to the one that is important for today, the C-instanton, which is both Dirichlet in the time direction and also in the Liouville direction. So again, it's fixed in both directions. Here, the picture that we've been drawing here. And there's only one collective coordinate, the time at which the instanton happens. This one, as we see, this is already fixed in space, so there's no collective mode. There's no collective mode for it. Well, one quick reason to see that is that the Liouville wall already breaks Lorentz invariance in this direction, the space direction, so we don't expect a collective coordinate for it. There's only one. Okay, so as we saw from the diagrams that we drew at the beginning, the main ingredient that we need is a 1-point function. And for this, it's a bit convenient for us to use the modular bootstrap approach, in which I'll remind you here with these two pictures, or more specifically, the modular covariance of the cylinder diagram depicted here, in which from the closed string perspective, we're computing a transition amplitude between these two boundary states, the CC boundary states, written here. And for the open string perspective, we're computing a trace over the Hilbert space of the open string. Now, a bootstrappy definition of what the CC boundary state is, or the CC boundary condition is is that this open string spectrum consists of only one thing, namely the identity, plus its various order descendants. So it's the simplest thing that it could be. Okay, so this one is the definition. And from this, so on the open strings, as we said, from the open string point of view, we're computing a trace. So we know this because it's just something like this. And since we know the right-hand side, then we can deduce what this function is from the left-hand side. So without doing the analysis, I'll tell you the answer, that this is just a sinh 2 pi p from this definition. Okay, now that we know the 1-point function, we're ready to compute already the simplest instanton corrections to closed string amplitudes. So for example, the one we drew at the beginning is the product of this 1-point functions. Now in the constants of c equals 1, as we saw in the previous slide, the 1-point function from the Lulu piece is just a sinh pi omega, also for the second one. And for the free boson, we just get the 0 mode, the collective mode here, x1. Okay, and then as promised, when we consider these two and integrate over the collected coordinate, we recover the delta function conserving energy, and it's just proportional, okay, to pi omega squared, sinh pi omega squared. And now this we can check, and indeed it matches what the matrix model will tell us, which I won't have time to explain. But if you remember, for the NPR formalism, we can efficiently compute these amplitudes exactly, and it by a formula like this, for those who remember, and it matches exactly this amplitude. So you see, in some ways,
providing the appropriate Hall reflection.
Yeah, provided we use the correct Hall reflection, the reflection of the Hall.
Could you remind us which one the appropriate one reflection was?
Yeah. So for c equals 1, the reflection Hall is just that of the particle to its inverse. I can write down the formula. Something like this. Okay. And this non-perturbative factors come from this piece, expanding this piece into this formula. Okay, so this is what reproduces this sinh pi omega. Okay.
Maybe just to mention that the perturbed piece has been implicitly summed using Borel summation.
Yeah, so this is Borel resummable into, well, doing the integral here, this. So this is why in c equals 1 we're a bit lucky that this expansion that I drew a couple of slides ago is actually unambiguous. Okay, and
is the Borel summability specific to this particular reflection choice, or is it the more general thing for other boundary conditions as well, discussed in NPR?
Let's see. So in NPR, it really just uses the same reflection phase, which is this formula. And yeah, I mean, for this one, you could check that this is Borel resummable, just using some properties of the gamma function. But let's see.
I mean, for more general potential, it certainly may not be. And we know that in quantum mechanics, generally, the semi-constant expansion may not be for us. But for this very simple potential, identify a piece that the Borel, it's Borel summable, and a part of it Borel is equal to its own Borel summation, and the instant correction is on top of that.
So on top of this. Yeah, so for more general potentials, well, one we have to check, but there's no reason to expect the Borel resumability, at least to me. Okay, so this was simple. And we can also do the 2-instanton case, which is not too bad either. So the picture should be something like this. It closely comes in here, closely comes out. And now, again, we have this non-trivial dependence on the distance between the 2 instantons. And we already drew these diagrams above. So this could end on the first instanton or one in each, all 4 possibilities. And then again, we have this measure that we talked about earlier, connecting these two. Okay, so now we're also in pretty good shape to compute explicitly what this measure is, to see that it actually makes sense. So we can compute the cylinder diagram, which depends on the separation between the 2 instantons, as in here. And for instance, this is the Liouville piece, as we said. This is just a 1,1 degenerate character here, which we described above. This is the free boson piece. And this is the BC ghost piece, which as usual, they cancel 2 sets of oscillators worth. Now the remaining integral is pretty easy to do, and then you get this function here. And this is the measure I was talking about. So this is, again, so one of them gives you, roughly one of them gives you the delta function conserving energy, and the other one is the integral we need to do. And of course, we need to include this measure. Okay, so the integral one has to do is of the following form. In instanton moduli space, the separation of the instantons. And the last thing we need to specify is, as you can see, there's a pole here. We need to specify a contour prescription to do these integrals. And it turns out that, so the correct contour prescription we should do is this one in blue, which I drew in Euclidean signature. Or equivalently, by rotating the contour, we can do the Lorentzian one, which is how we phrased it in the paper. And as you can see, for instance, if we wanted to do time reversal, we would have to flip it to go in the other direction. So we'll pick up some poles. So what I'm trying to say is that this choice breaks time reversal symmetry, which is in good shape, as we, from the matrix model, the vacuum that we choose is by only filling these eigenstates, which have incoming flux from the right, but not from the left. In other words, just filling one side of the potential. So this choice also breaks time reversal symmetry, and we can see it from the wall sheet in the choice of this contour.
Sorry, Victor, can I ask a question here?
Yeah, go ahead.
So is this really a good vacuum? Isn't the Fermi sea slowly depleting? Because there are fermions tunneling from one side to the other with this choice, right?
Well, yeah.
So there are that are flowing.
Yeah, so the way I built this, this is just a picture, but the way to build this is this is an energy eigenstate, right? So it's stationary. So we use it by solving the Hamiltonian. So what I say is that you only fill this energy eigenstates up to the energy of negative mu. So it's an energy eigenstate, so it's stationary. It doesn't leak, at least a vacuum.
Okay.
So in other words, what's proposed to be a closed-ring vacuum is leaking all the time. So you imagine
Exactly.
Hi, I have a question about the breaking of time reversal symmetry.
Uh-huh.
So in the modular bootstrap derivation of the ZZ boundary state wave function, actually only the absolute square of the wave function appears, right, in the cylinder amplitude.
Yeah.
So it's undetermined up to a p-dependent phase, which I guess, I don't know, I kind of always assumed that time reversal fixed the wave function to be, time reversal symmetry fixed the wave function to be real. But I guess once we're breaking that, is there a sort of principled way to understand why that's the only wave function we can think about? Why aren't there other instantons with some p-dependent phase in there?
Yeah, let me Yeah, let me go back to
wait. John, you mean a sign, not a phase, right? I mean, these things are supposed to be real. All the structure constants are real. When you normalize the vertex operator, appropriately, everything is real. There's no room for complex states.
Yeah, that's true. And also, this is not the only condition. We also have conditions between 1, m, n. So maybe that already fixes even the signs. But yeah, that's true. So these should be real. Again, so there's.
Sorry, why does it have to be real? How do I see that?
Well,
the sequence 25 data series is a unitary CFT, and these at least the Z1 1,1 boundary condition is in fact unitary boundary condition. Perhaps one might be confused by the DOZZ formula, because if you look at DOZZ paper, the formula actually doesn't look real, but that's just because the vertex operator is normalized in a funny way. If you normalize the vertex operator in such a way that the 2-point function is a delta function, so VP prime 2-point function is delta function and PMP prime, then actually the structure constants are all manifestly real, and which is what it should be, because this is a unitary 2D CFT. And there's no funny phases at the end of the day when you any of these correlators. When you decompose into conformal blocks, all the coefficients are real.
Is there if I were demanding that it were, if I were using it as a unitary quantum system, I would agree that we have to have that. But from the worldsheet point of view, is there a reason that we require that?
Not obviously. In fact, these other type of this M,1 Z boundary condition Victor was going to mention are not unitary. So no. But what I'm saying is that the Singer diagram is the square. It's not a Mott square. It's literally the square, because that's by the usual rule of the conformal block decomposition.
In a unitary theory, I agree. Yeah.
So one question. So you can also derive this 1-point function from, I guess the way they did it in the paper was with this Teschner trick. I mean, besides using the modular bootstrap.
Yeah.
In that approach, there is no ambiguity, right? If I remember correctly.
Actually, I like this modular bootstrap a lot more. Whoops.
There's no ambiguity of the sign. The reason is because, if you only look at the cylinder parent function, you would say that there's a sign ambiguity, but that would not be compatible with the factorization of this 2-point function and things like that. Because you factor disk into 2 disks, and there's no obvious. Otherwise, you would have said that you can flip the overall sign of the Z boundary state, but that's not true. That would not be a consistent boundary condition if you do that.
All right, thanks.
Okay, so thanks for the question. So the claim is that we see this breaking of time reversal invariance precisely in the choice of contour in instanton moduli space. Okay, so then we can just compute, having all the ingredients ready, you compute this integral, and you get some answer here. I guess the one last surprise is that this is not enough. We in fact need the higher action CC instantons, which are defined in terms of the higher CC boundary conditions. Only the M,1 though is the ones we need. So for example, to order E to 2G string, we need the 2,1, whose 1-point functions is similarly derived to be essentially 2 pi omega. And once we include those, we match the matrix model. Okay.
The reason to include them was to match the matrix model rather than some principle from the string theory perspective.
Yeah, exactly.
Wait. We know that there were these boundary conditions in trivial theory, right? So
I thought there were more general ones than this as well.
That's also true. So in principle, one might have to include all of them, except that you don't know the normalization, right? So
okay, let me rephrase the question. is there an interpretation of the other ones from the matrix model perspective, or a speculation?
I have no intuition of why this is the case. So the claim is that, okay, you should include everything that is possible. But one way to phrase it is that the normalization constants here are 0 for the ones that are not of this form. But I don't really have a good reason for that, at least so far.
I mean, we don't have any principle to fix the overall normalization for a contribution instant of a given type. Just, you know, in principle, there's no.
But the matrix model has a reason.
Yes, of course. I mean, if you assume the duality, yes, then you can fix it, which is what we did. And in fact, you would have you could complain about the same thing, type 2B, superstring theory in 10 dimensions. In that case, from the worksheet perspective, there's also no a priori way to fix overall normalization. But it turns out if you demand S duality to hold, which which is similar to plays a similar role as you have to do with the matrix model here, then in type 2B you can fix normalization.
Can I ask one question also here? Have you considered the same problem in the 0B theory when you have both sides of the Fermi field?
Yeah, we have, and I was hoping to talk about it, but given the time, I don't think I'll have. But I'll flash pictures so that you can see roughly what's going on. But yes,
you can say something in the discussion.
Yeah, we can also save it for later. Okay, so just want to lastly mention that this, well, assuming that only these guys contribute, we can check to all orders for arbitrary n, the multi-instanton one, leading order. Okay, so yeah, okay, so here's the picture if you want. We can just discuss it later, but in 0B, the D-instantons are actually charged. So here I denote the D-instanton by red and the anti-D-instanton by blue. And of course, now the boundary states have an NS factor and an R sector, RR factor here. You read the charge by just sending the momentum to 0. One of them has +1, the other one has -1. The interpretation is that the D-instanton represents tunneling of the particle. So remember, the particle whole pair is a closed ring, and the tunneling of the particle is mediated by the D-instanton, and the tunneling of the whole is mediated by the anti-D-instanton. And of course, you can play the same game, and we have some preliminary evidence that this works.
Is there any evidence of Fermi statistics from this perspective?
For what perspective? For the statement that I just made?
The fermionicity of the, is the anti-commuting nature of fermions or anything like that. Do you see that from the string perspective? That if you put two on top of each other, they annihilate?
I don't think so, actually. I don't think I could see that from purely from Walsh-sheet.
Isn't that in the annulus amplitude that gives the measure factor?
Well, from the measure factor, I can read, for example, the one they have opposite charges, but not the fermionicity.
Don't you get the Vandermonde that the eigenvalues should satisfy from somewhere?
Oh, very good. Yes, thank you for reminding me that. Yeah, that is indeed true. That's one good way. Where did I write the measure? Yeah, so indeed the measure was here. But that's, I guess, a Vandermonde in some sense it's just like the non-abelian natureness, I guess, of the d-branes on top of each other. But yeah, so the statement is that if you look at when the separation of the d-instantons goes to 0, then this just behaves like a delta x squared, which is reminiscent of the Vandermonde determinant, as Emil mentioned. Okay, that's one piece of maybe a clue of where to see this. But more microscopically than that, I'm not sure of the Walsh-sheet.
I think in the sort of revival in the early 2000s, there was some discussions, maybe in the Seiberg-Shi papers. I can't remember. Maybe Igor remembers better. anyway.
Mm-hmm. Okay, so this is probably a very good place to stop here, and just maybe pause for a couple questions and just so that we can let Minjae take over now. Thanks.
All right, thank you, Victor.
Thank you.
Well, actually, maybe we can go immediately to Minjae's talk, unless there is an urgent question. Does that sound good to everybody? Okay. So maybe Minjae, can you share the screen?
Yeah, let me start.
Okay, so.
Does everyone see my screen?
Yes.
Good.
Right.
So, hi everyone. Hope you're staying safe and healthy. I wish to first thank the organizers for hosting this wonderful workshop. I'm having lots of fun. And also, thank you, Victor, for a nice talk. I'm going to tell you about a work that I've been doing with my collaborators here, Nathan Agman, Bruno Professor, Victor Rodriguez, and Sheen. And it's basically D-instanton in type 2B superstring. But my talk today will be like more geared towards string field theory aspects for D-instantons. So I have to say that like string field theory framework in the context of D-instanton was fully developed by Ashok Sen over the last 1 year. So if you are wondering about the full details in the bosonic case, you can look at either Sen's lectures or his series of papers, including this one. So I'm here as a young, like humble but enthusiastic student who's recently been actively learning his work in order to apply it to the setup of interest, which is type 2B superstring. And the upshot is that string field theory provides appropriate framework to study such problems. And let me motivate by some of the clues, which tells us that actually we need string field theory to do the D-instanton perturbation theory. So first of all, typically in string perturbation theory, if you study Veneziano amplitude or Virasoro-Shapiro amplitude, you run into divergences, which is coming from some degenerate limit of the Riemann surfaces. And these divergences actually are remedied by analytic continuation in the momenta. That's where you get all those gamma functions, right? But the thing for D-instanton is that it doesn't have any non-compact directions, meaning that regarding the open strings on the D-instanton, they're really discrete and they carry no continuous momenta, which you can analytically continue. So the usual trick of analytic continuation simply is not applicable here. So when Victor mentioned that logarithmic divergence, that is just absolutely there, and you simply don't know how to deal with it in any unambiguous way in the usual string worship perturbation theory. But the upshot for string field theory is that it properly divides moduli spaces. And in particular, for the moduli space corresponding to such degeneration limit, it correctly replaces that by appropriate Feynman diagrams. And it actually renders the results finite and unambiguous. So that's the first sign that string field theory is needed for D-instanton. And there's another, a bit of technical subtlety for D-instanton. If you recall, like usual, like Polchinski string theory textbook, let's say, all the worship computations are actually done in so-called Siegel gauge, where you require that states are annihilated by zero mode of the Beagles. But it turns out that that choice is actually singular for the D-instanton case. I'm going to elaborate on this later, but the idea is that from the point of a string field theory, which is formulated in BV formalism, Siegel gauge simply is a singular gauge choice, and you can choose some alternative gauge, or more appropriately speaking, appropriate like alternative Lagrange submanifold. And also, in Victor's talk, we ran into the issue of this instanton zero mode, which is propagating. String field theory correctly deals with this, including the subtlety of possible field redefinition. And there are several more aspects where string field theory plays key role. So here are my main statements, okay? First, string field theory is a must for D-instanton, at least for now. We don't know of other alternative ways to unambiguously do the D-instanton perturbation theory. Okay. But hopefully nobody left because I'm talking about string field theory. I want to tell you that you don't need to get scared. Okay. String field theory might sound like a monstrous construction, but in practice, all one is doing is just usual 2D CFT computation. And I'm going to, in the end, like give you very simple string field theoretic computation, which actually gives non-trivial contribution to our computation. So is there any questions so far? I'm just trying to convey the message that we need string field theory.
Do you need anything out of string field theory other than how to partition the moduli space of the world sheet?
Yeah, so for example, this issue of Siegel gauge, and also the possibility of field redefinition. Yeah, there are many subtle issues which usual string perturbation theory actually is simply blind.
Okay.
Yeah. Good. Let me first introduce the setup of interest. And it's the simplest setup, which is standard textbook material. It's usual type to be string in flat 10D. And this was actually discussed at leading order by Green and GoPro more than 2 decades ago. And somehow people didn't continue the sub-leading order computation. So as usual, there are free boson, free fermions, and BC beta gamma ghost system. So I'm working in NSR formalism. And as a grad student, you basically, the first thing you compute is things like 4 graviton scattering. But as Victor mentioned, now if we introduce the instanton boundary condition, which is Dirichlet in all space-time directions, all closed string scattering processes receive contributions from such diagrams involving the instanton boundary condition. And here is such an example. This seemingly disconnected pieces is a correction on top of this tree level thing. So we are going to consider a single D-instanton for now. Multi D-instanton is very complicated, I think. So we are just going to consider this. So as Victor mentioned, there's this e to the minus 1 over gs, D-instanton effect. And this is the leading order computed by Green and GoPro. And this is the piece we are interested in. Okay. Already mentioned in Victor's talk, as we put the instanton in some space-time point, it manifestly breaks translation symmetry. So how is this manifest at the level of the worldsheet? The associated zero modes arise as the open string state, which is this one here. So there are 10 of them. And just like any other D-branes, the instanton is also half BPS, which means that it preserves half of the SUSY, but it also breaks the other half of the SUSY. And the zero modes associated with those, are given by these spin fields. And there are 16 of them. And these zero modes, or instanton moduli modes, have to be integrated over the instanton moduli space. So how do we usually do this at the level of worldsheet? Well, for the bosonic moduli, whenever you have diagrams like this, where closed string has some momentum k, let's say, there is this e to the iky factor coming from the doubling trick, where y you can interpret as the position of the D-instanton. So once you integrate over the position of the D-instanton, you recover the momentum conservation. For the Fermionic ones, because they are Grassmannian, now you need insertion of 16 broken supercharges. So to the diagram of interest that you want to compute, you have to find a way to distribute 16 broken supercharges. And this is the precise computation that Green and GoPro did. So here, each of the closed strings are graviton. There are 4 of them. And you distribute 4 supercharges on each. And each of them evaluates to something like this. It has some structure. And there's this polarization together with the 2 factors of the momentum, which is nothing but the Riemann tensor. And this basically gives e to the 2 pi I tau type contribution to the r to the 4th term in type 2b Sugra, where tau, if you forgot, is the combination of the axion and dilet. But as you can notice here, this doesn't have any higher momentum expansion. meaning that this really stops at r to the fourth term. So, which means that you can actually compute this also using the type 2b supergravity, and that's also what Green and Gopro did in their paper. So, precisely speaking, all they did was really to fix the overall normalization for this single instanton contribution, which worship theory doesn't know how to fix, but they basically go and fix it. So the real stringy thing starts at the subleading order. And these are the diagrams that we've already seen in Victor's talk. And we are going to consider the computation with delta, 2 of deltas and 2 of delta bars. By the way, these are linearized fluctuation around some given tau background. And of course, these are the same as for graviton via supersymmetry. Is someone speaking? Okay. Okay. So the reason why we deal with this is to simplify the complication with the insertion of these spin fields. The idea is that when we have spin field insertion, we can deform it into the bulk to basically apply the SUSY transformation. So it will act as a lowering operator in the SUSY multiplet. So once you have 8 of them, this delta bar will turn into delta. And this diagram is literally some number times this e to the iky. And you can play the similar game for the other diagrams. Okay. So the upshot is that even though you might think that there are many ways to distribute like these 16 supercharges, in the end, they all reduce to just diagrams without supercharges, but all the closed strings being delta. Okay. So this again was the leading one computed by Green and Gopro. And these things are now the subleading terms. And with some picture assignment, so again, in superstring, picture assignments are important. But with some picture assignment, you can compute this to be 0. There's some Jacobi abstruse identity involved. And this thing gives somewhat non-trivial looking result. So first of all, you see this epsilon. Epsilon is the cutoff we just arbitrarily imposed for the logarithmic divergence, which already showed up in Victor's talk. And there are other momentum dependent terms. And especially there's this digamma function. Okay. And this digamma function actually has poles corresponding to massive string states. Which is obvious because you can consider the OP limit of these two, and then they can produce massive states. So you need to consider basically summing over all the 4 positions of these 4, and then integrate over this bosonic moduli to impose the momentum conservation. And this is the result you get. Okay. So let's first look at, by the way, the cutoff dependence vanished because you get simply S plus T plus U, which is 0. So you might say, oh, it seems like we don't need to worry about divergences here. Well, that actually turns out not to be the case. Anyway, let's look at these terms. You want to make some comparison with already known results. So what you can do is to compare this with low-energy expansion. So if you expand in small st and u, you get this type of terms. And this term gives contribution to D4R4. And this term gives contribution to D6R4. And these non-trivial numbers like pi squared and Riemann zeta evaluated at 3 perfectly matches with conjecture formed by Green and Gopro. They conjecture the form assuming the S duality, supersymmetry, and the presence of the instanton corrections. But they agree. So we actually wanted to declare victory and publish the paper. But then we realized that there's a piece of the result which never matches the expectation, which is this constant piece. So this piece actually must be 3/16 purely from supersymmetry consideration. I forgot to write the paper. This, for example, you can look at the paper by Yifan Wang and Xin, where they use supersymmetry to fix this constant. I mean, they get the differential equation that the coefficient of the R to the 4th term must satisfy, and you can derive this constant. we've tried to come up with some ad hoc resolutions for this mismatch, but we couldn't. And when Ashok-san started to write all these wonderful papers about string field theory for D-instantons, we realized that we actually need string field theory. So the upshot is that string field theory computations will actually give rise to extra constant contributions. And we are still this is still work in progress, so we are not here yet, but we are getting some plus contributions to hopefully turn this into 3/16. Any question on this setup? Okay, with that.
Just to mention, I think the conjectures were not made by Green and Guthbro. I think it started Green and Steffi, and later I don't think I don't think Green and Guthbro made any statement about.
Oh, sorry. Yeah, actually they made conjecture only about the R to the 4.
Yeah.
Oh, yeah. Sorry. Oh, my bad. Yeah, there should be name of like SETI and others. Sorry, my bad. Yeah, I was being too quick. Yeah. My apologies. So with that, I'm going to give you a brief introduction to string field theory. For more complete details, you can look at Sen and collaborators' papers. For example, this is a nice review, which any graduate student who's taken first semester string theory can read and penetrate through. Believe in my words. And this is an open-closed superstring field theory paper, which basically is the framework that we have to be working. So when I say field theory, when we say field theory, what we mean is off-shell fields. So first, we have to reflect on what we meant by on-shell fields. Okay. In string perturbation theory, what we meant by on-shellness was simply the BRST closedness. So all the states of Walsh CFT, which are BRST closed, we call them on-shell states. And that's how we determine the spectrum. And those are the states of which we compute the amplitudes. So a very natural thing to do when you want to define what you mean by off-shell fields is simply to get rid of this condition. Okay. So when you declare is the following. Okay, by string fields, I mean all states in my CFT, Walsh CFT. Okay. Modulo some technical difficulty, technical constraints, which I'm not gonna elaborate on. Well, roughly speaking, you simply get rid of this thing, and then you consider all states in your CFT. Okay. So you define off-shell fields. Now we want to define off-shell amplitudes. There's a very natural thing to do. These are just states in your CFT. So there is no problem computing their correlators. So you simply compute the correlator of the string fields and integrate over the corresponding moduli. That's gonna give some result. And that's a very natural definition of off-shell amplitude. And when these are on-shell, that agrees with what we meant by on-shell amplitudes. But there is a subtlety, which is that when you actually do actual computation of the CFT correlator computation, you actually have to specify the coordinate system choice. Okay. And the result of this computation actually differs when you choose different choice, when you make different choices of coordinate systems. So you might say, how is this consistent at all? Well, the option is that we are doing field theory. So if any ambiguity you run into can be resolved by the field redefinition, you're fine. And all the on-shell quantities are well defined. And that actually was shown to be the case by string field theorists. So the option is that, okay, you just work with whatever coordinate system you want to work with, you get the answer. Whenever you compute on-shell quantities, that's not going to depend on your choice. Okay. So let me give you some example of the ideas in the simplest setup of bosonic closed string field theory. So we start with 3-point, okay? So we are doing Feynman diagrams now. So we want to define what we mean by 3-point vertex, okay? We know that moduli space of 3-puncture Riemann sphere is 0-dimensional. So that's why we represent by this X. So this is a point representing the 0-dimensional moduli space of 3-puncture sphere. And over that, we are going to draw a fiber. This fiber is infinite dimensional, and it stands for the choice of coordinate systems. modulo phase rotations, which I'm not going to talk about. So you might say, okay, I can choose this coordinatization versus some other coordinatization. You can choose whatever you want. They are related by field redefinition. Okay. So say you chose this one. That's your definition of 3-point vertex. Okay. So in practice, what you do is simply you compute 3-point function using coordinate choice you made here. And that's gonna give you 3-point vertex. Is this clear? So once you are at this point, now you wanna do what you do in usual QFT. You wanna draw Feynman diagrams. Okay. These 3 diagrams are one you can do with 2 3-point vertices. But you have to define what you mean by propagated here. And there's a very natural construction from the Riemann surface point of view. So each of the vertex, you have 3 punctured spheres, and you have some local charts which you defined when you made the choice of the vertex around these punctures. And you simply plumb them by identifying 2 charts by some family of parameters. This effectively makes a tunnel between these 2, and this entire thing becomes a 4 punctured sphere. Okay, so that's what we mean by this. And in particular, it's important to keep in mind that this does not correspond to a single Riemann surface, but rather a family of Riemann surfaces parameterized by S and theta. Okay. But importantly, this gives not just the surfaces, but there is a coordinate system induced by the previous choice of 3-point vertex. So this thing naturally comes with its own coordinate systems around these punctures. So this is a picture for the 4-puncture sphere. We know that it's complex 1-dimensional. Let me suppress 1 dimension, real 1 dimension. So there's our favorite cross ratio Z. And each of these diagrams will cover some neighborhood of 0, 1, and infinity, where the vertical direction, again, is the choice of the coordinatization. But unless you are in a very special situation like Witten's cubic open string theory, it's going to be the case that these diagrams alone, these Feynman diagrams alone, will not cover the moduli space exactly once. So you have to fill in the gap, the leftover. And there's only one Feynman diagram that you can associate with it, which is 4-point vertex. Okay. So here you make a choice for this 4-point vertex. This is where you define what you mean by 4-point vertex. Okay. And there are many choices you can make. You can either make it like this, or you can have something like this. But there is a condition that coordinate choices have to match between the boundaries of different Feynman diagrams. That's related to the null-state decoupling. And if you want to look at the full, like all-order solution for such construction, you can, for example, look at my paper on open-closed hyperbolic string vertices. But in practice, for our consideration, we are just gonna build vertices up to the order we are working with. We don't need to worry about higher orders. Any questions so far? So all I'm saying here is that you define like vertices in such a manner that they basically agree at the border between different Feynman diagrams. Okay. So space of string fields is huge. We are basically taking all the states in CFT. Okay. But magically, it perfectly fits into the formalism of BV. And the major success and major works that was done in string field theory community over the last 3 decades by great theorists like Barton Zuiba or Ashok Sen was really to show that this formalism fits well into BV. Okay, that was their major contribution. And the open plus closed superstring field theory constructed last year, was in some sense a good completion, because we are in the situation where we want to apply that to our context. And just like any BV formalism, we need to make a choice of Lagrangian submanifold. Oh, by the way, if you're not familiar with BV formalism, you can think of this as some generalized version of BRST or Faraday-Popov gauge fixing. And BV formalism basically is like where the structural constants may depend on the fields, and also the algebra doesn't need to close like off shell. But there's a, yeah, it's very natural generalization of usual BRST. So usual worksheet computation corresponds to Siegel gauge, as I've already mentioned. So yeah, when you impose that your fields must be annihilated by these zero modes of the B ghost, that's where you make the choice of the Lagrangian submanifold. So say you made some choice of Lagrangian submanifold, and you're left with some complete set of states for open and closed state. So any open string field and any closed string field can be expanded in terms of them. And there's some coefficient. And to be precise, these are what we must be calling string fields instead of the state. But yeah, we actually use the like terminology interchangeably between the two. And BB formalism tells you what the path integral should be looking like. So the path integral, the path integral looks like this. So you have to integrate over all these string fields, all these coefficient fields. Okay. Well, you might say, how is this like integration over field? For example, when closed string carries momentum, this is actually a function of momentum, or in the Fourier transform version, is literally a field. So in that sense, these are really fields. But for D-instanton, these are all discrete, so they're literally some like number fields. And then you have some action, which is now gauge fixed. So the action must have kinetic term. So how do you determine kinetic term? Well, one way is that when you vary it, you want to get free equations of motions. And free equations of motions was nothing but cubic closeness. So that's the reason why kinetic term has this cubics. And then you have a whole bunch of vertices. So how do you evaluate these vertices? I already told you. You compute the CFT correlator in the coordinate choice that you made for the vertices, and you integrate over the moduli space corresponding to the vertex region, and use some of the topologies. Okay. So this is one you can compute using the data that I've already explained to you. So this is now putting string theory at the same footing as a QFT. And this will provide us key insights into the study of D-instanton. Any questions so far before I move on to D-instanton? I hope everyone's following. Okay, let me move on. So now we have to discuss string field theory for D-instanton. First of all, as we've already said, there's no non-compact direction, so all the open string fields are discrete. Okay. Let me actually skip this discussion for the interest of time. And second aspect is that Siegel gauge is actually singular for something called ghost zero mode sector. So what is this sector? All I mean is that we consider the weight zero modes. Okay, so these are weight zero states with just pure ghost oscillators. And all such states, there are only 4 of them. You can write all of them. In the BV, in the usual BV, these are the fields, and these 2 are the anti-fields. But Siegel gauge actually fixes this one and this one to be 0, because they are not annihilated by B0. So you're left with these 2 fields. Now, you compute the kinetic term for these fields, and you actually get the kinetic term is 0. So these 2 have 0 kinetic term, meaning that they actually lead to divergences in the worksheet computation because their propagator is infinite. And this actually arises in the C equals 1 story, like for the NOS 1-point computation. There actually is a divergence you run into because of this. So one can choose alternative gauge or choice of Lagrangian submanifold, which is the original field and anti-field. So you put these two to be 0, and you're left with these two. So I told you that this thing had 0 kinetic term, so it still looks singular. But the upshot is that it actually completely decouples from the action because of the ghost number conservation. Roughly speaking, it's just that this thing has, so because we killed this, this thing no longer has something to contract with. Sorry, this thing no longer has something to contract with. And what about the other ghost zero mode? So this is from now on what we will mean by ghost zero mode. You can evaluate the kinetic term. It gives a finite constant piece. Okay, so for example, when you compute official amplitude, some amplitude like this in particular will involve Feynman diagrams where you have this vertex, and these two vertices are connected by some propagator. And we must include this ghost zero mode contribution. Okay, so in practice, the computation is that you evaluate this, multiply by this propagator. And similar contribution also exists for the annulus, which, for example, you can have this vertex with closed open, and then you can consider the propagation of the open.
Does this slightly different choice of gauge amount to a proper treatment of the supermoduli?
Okay, I have to tell you, we actually don't have a good consistent formulation of string field theory regarding the super Riemann surfaces. So I don't have thing to say about that.
Well, but it looks like your gauge choice amounts to asking that some Fourier mode of beta annihilates the states.
Sorry, what do you mean by Fourier mode? We don't have any momenta here.
No. I mean.
You mean oscillator?
Oscillator mode.
That is. Let's see.
You're basically saying that beta 1/2 annihilates.
Yeah, we are saying that basically we don't want gammas.
Right.
Maybe. Oh, that's a good point. I actually never thought about it that way. Maybe. Yeah.
Okay, maybe we can talk later on Slack.
Yeah. Yeah, I didn't think about it, but yeah, that's true that. Yeah, maybe.
Okay.
Yeah, thanks for the question. So let me do this computation. Okay, this is gonna actually give us some extra constant piece, which we were missing in the previous naive Worley computation. So in order to talk about this, we have to define what we mean by this vertex. So we have NS in the bulk and NS at the boundary. We parameterize this surface by Z in the upper half plane. Bulk point, we put an I. But we are not going to specify the coordinate choice around the bulk because they are always going to be unshelled for us. But for boundary point, which we put at 0, we actually have to make a coordinate choice. So we are going to make a simple coordinate choice where W is the local chart and it's related to the global chart by simple rescaling, lambda. So roughly speaking, when lambda is large, it's covering very tiny region around this puncture. And I didn't mention about this before, but in the case of superstring, one always has the issue with picture changing operators. And actually, in the fiber that I discussed before, one also has directions along which one has to specify the picture changing operator locations. So that's also part of the data defining the vertex. So here I'm simply defining that we put one holomorphic PCO at the bulk point. And this completely determines what we mean by this vertex. Okay. And then we can compute. So this was delta. This actually gets contribution from the dilaton part of this diagram. So we have dilaton in 0, -1 picture, and we have this ghost zero mode, which we were talking about before. And this is where somehow non-trivial contribution from the Ada ghost comes in. So in textbook, when you actually look at the zero picture dilaton operator, people just write partial x and like fermion term and do not write extra terms. But actually there are extra terms which people somehow omit all the time. That's because in the picture changing operator, there's like operator which looks like e to the 2 phi, partial eta, e, and e to the 2 phi, total derivative of, I think, sorry, total derivative of e to the 2 phi, eta b. This term is actually present in picture changing operator, but somehow people never deal with it. But it's there. And in particular, this thing includes this term, which is important for us because this ghost zero mode written in the operator includes this weird ghost. So as you can see here, you have non-zero contraction between these two ghosts, and all the phi ghost numbers correctly adds up to -2. So you get a non-zero number. And this gives non-zero contribution to this diagram, which we actually didn't capture before in the naive string perturbation theory approach. Let me skip this discussion for the interest of time. Yeah. I guess I should stop after discussing this. Okay, ghost zero modes are not the only weight zero modes in the open string field sector. There are the usual bosonic and fermion instanton moduli modes. Okay. So let's look at how they appear in the string field path integral. They appear in infinitely many diagrams, but I'm just here writing down some of them. So first, we have integration over these fields, y and epsilon. And you have all these diagrams where you can have arbitrarily many insertions of y's or this mode. And what they do is that they simply bring down a power of momentum for the closed string. So these things, once you are evaluating expectation value of some quantity, is what gives the e to the IPY type dependence. Okay. So from this point of view, it's obvious that we are literally integrating over the instanton moduli, the bosonic one. For the fermionic one, we again have a whole bunch of insertions of this epsilon. But this epsilon is Grassmannian. So we simply pick up the term with e to the 16th. And this is the reason why before, when we were doing naive worksheet approach, we were actually distributing 16 broken supercharges over the diagrams. And there's also another insight we can get from this formulation. So y and epsilon, okay, by the way, we are choosing single gauge for all the sectors which are not ghost zero mode sector. Okay, so those are usual string theory. But in such a choice, these two modes actually has no kinetic term. That's because they are of zero weight and they obey single gauge condition. So you might say, oh, does this mean some singularity? That's not the case here. Okay, the interpretation is different. Just like in usual QFT, okay, in usual QFT, when you have zero modes for the some instanton background, they are not propagating degrees of freedom. Okay, they are not propagating degrees of freedom. Rather, they appear as a background fields which you must integrate over, just like what we are doing here. And in particular, it means that there is no log divergence from this zero mode propagation because they do not propagate. They are not propagating. We don't have kinetic term. They do not propagate. And such diagrams are simply absent. So before, when we were saying that like in diagrams like this, when we have this zero mode propagating, in the full-fledged string field theory language, such diagrams are simply absent. And there is no logarithmic divergence. Is this clear? So as you can see here, string field theory really gives us natural way to understand where, like, you know, how you've gone wrong in the naive worksheet theory approach and how to correctly take into account all the rigors. There is a subtlety. This actually contributes to further constant terms that we are after. The subtlety is that these two modes actually are not exactly the translationers SUSY. They are rather related by some field redefinition. And field redefinition actually involves a closed part which depends on the closed string field. But I think I don't have time to discuss that. But the upshot is that this is something you have to compute, and this is also going to give some non-zero finite contribution. Let me skip all of this. I mean, I wanted to give you some details about how all these vertices are constructed, but I think I have to skip them. Okay, let me just summarize. So I hope that I conveyed you the message that string field theory provides proper framework for D-instanton perturbation theory. At least for now, I don't know of any other alternative approach which is rigorous and consistent. So for example, instanton moduli modes, as we've just seen, is treated just like the usual QFT. And also divergences are absent. And we also saw like the issue with the gauge choice and so on. So this is still work in progress. We've completed the ghost zero mode computation. We are done with this computation. This field redefinition, we are done. There is further issue with rigid U1, which I didn't talk about. And also on top of that, there is issue of something called vertical integration. This actually is important, so let me just briefly mention it. So I told you that in the superstring theory, field theory, the choice of vertex also includes choice of the location of PCO. So let me say you have this type of diagram for some moduli space. Oops. And say when you have some different Feynman diagrams, you may well run into the case where PCO location do not agree. So you want to close the cycle. So you have to integrate along this vertical direction. This actually happens very frequently, even at the order we are considering. And this is rigorously and consistently formulated by Ashok Sen and Edward Wheaton about 6 years ago, I think. So yeah, this is a very exciting playground to test all these ideas that has been stated in a rigorous sense, but never showed up in like any practical computation so far. I didn't write open questions. Like obvious open questions will be like, what about multi-instantons? What is the role of IKKT matrix model and all of those? But I think I have to stop here for questions. Thanks.
All right, thank you, Minjae.
Thanks.